Right, in this tutorial we're looking at section 11.5 on chemical reactions and dilution problems. Okay, so for these we have input and output mixing problems. Okay, so there's a fair bit of information that we need here. So we have V0 is the initial volume in some tank or container that we're given. Okay, A is the mass of a dissolved substance in kilograms. B is the mass of a dissolved substance in a second solution in kilograms. F is the rate at which the second solution is being added to the container in litres per minute. And G is the rate of solution is leaving the container. So essentially we're going to have a container of some description. Okay, that's got some sort of concentration to it. Okay, we've got volume coming out, but then we've got volume of a different solution going in. Okay, and that solution's got a different concentration to the solution that we've got. And so we're looking at finding the concentration of the solution at any time. Okay? And Q is the amount of dissolved substance in the container at a time t minutes. Okay, so that means that we get the differential equation dq dt equals bf minus qg on v0 plus f minus g times t. And we know at q0 that's equal to A. Concentration C is found by C equals the mass divided by the volume. Okay, is the other thing that we need to know. Okay, if we're talking about input and output flow rates, okay, this is another example of bounded growth or decay model. Okay, this occurs when we're saying F equals G, so that means that our concentrations are the same. Okay, and this is an example of separation of variables. Okay, so that's our example where we have dy dx equals f of x times g of y, and so we get the integral 1 over g of y dy equals f of x dx. Okay, chemical reaction rates. In a chemical reaction, the rate at which a new substance is formed is proportional to the unused amounts of the reacting substances. Okay, so when we have lots of our unused reacting substances, then our reaction takes place quite quickly, but as those disappear or get used up, then our reaction slows down. Okay, so that would make sense. So we've got a few worked examples that we're going to have a look at. So I'm going to look at worked example 9 to start off with. Okay, again, like in a lot of the sections in this chapter, the worked examples are quite wordy, so don't worry about writing them down. So you have a tank that has a capacity of 300 litres and contains 200 litres of water in which 100 kilograms of salt have been dissolved. A salt solution of concentration 2 kilograms per litre is poured into the tank at a rate of 3 litres per minute, and a well-stirred mixture flows out at a rate of 2 litres per minute. Okay, we need to state the differential equation for Q, okay, the amount of salt in kilograms in the tank after t minutes. So what we need to have a look at, okay, is, well, we can say our initial volume in the tank, okay, our V0 is our 200, okay, we have 3 litres a minute in and 2 litres per minute out. Okay, so what we can say is we can create an equation V of t, so that's our volume at any time. Well, that's going to be equal to 200, okay, plus it'd be our 3 minus our 2t, because we've got 3 out, 2 in, so that means that we're going to get 200 plus t. Now the inflow rate is the concentration times the the inflow rate is the concentration times the inflow volume rate. So our inflow rate of our material is going to be our 3 by our 2 kilograms per minute, because it's 3 litres by our 2 kilograms per minute. Okay, our outflow rate will equal 2Q, now remember Q is concentration in the tank at any time, okay, over our V of T kilograms per minute. Okay, and our dq dt, well, that's going to be our inflow rate minus our output rate. So that means that our inflow is going to be, we've got our inflow here, that was going to be 6, okay, take our 2q over our v of t, which is 200 plus t. Okay, we also know when we've got q of 0 equals 100. Okay, so to verify our solution, okay, so what we need to do, okay, is we've got state our differential equation. So we've got our differential equation here. Okay, for part B, what we need to do is verify. I might just go a different colour for this. So verify that q equals 2 outside of 200 plus t plus c over 200 plus t squared. Okay, we need to verify that's a general solution to the differential equation. Okay, so what we need to do to verify that it's a solution is put it into our index form. So we can say, well, q equals 2 outside of 200 plus t equals our c, not equals, plus our c outside of 200 plus t to the negative 2. Okay. What we need to do is we now need to differentiate the given solution as the left-hand side. Okay, so what we need to do, okay, is find out dq dt. Okay, well that's going to equal 2 minus 2c outside of our 200 plus t to the negative 3. Okay, which we can write as 2 minus our 2c over our 200 plus t cubed. Okay, so what we can do is substitute for q into the right hand side of our equation. Okay, so when we're up here, okay, so we're saying this is our q value, so we're going to sub this in for our q value in our equation up here. Okay, so we're going to say then that we get 6 minus 2 over our 200 plus t outside of all of this, our equation that we had up here, okay, which is our 2 times 200 plus t plus c over our 200 plus t squared. Okay, when we expand that out, okay, what we get, okay, is 6 minus 2 times 2 outside of 200 plus t over our 200 plus t. Okay, take 2c over our 200 plus t cubed. Okay, we can simplify this down to 6 minus 4, take our 2c on our 200 plus t cubed, which of course is our 2 minus our 2c on 200 plus t cubed. Okay, since this is the same as what we had here, okay, then we can say that yes, it is actually a solution to the equation. Okay, for part C, we've got to determine the value of our constant C, okay, that we have. Okay, so we know that we've got when t equals 0, q equals 100. Okay, so that means that we've got our 100. So we're talking about using our equation. Our equation here. So I've got to label them so I can track myself. So I'm going to use our equation here, our q equation. Okay, so we're saying that our q then, okay, is going to be our 100 equals, will be 2 times 200 plus our time t of 0, okay, plus C over our 200 plus 0 squared. Okay, so that means that we get 100 equaling 400 plus C over 200 squared. Okay, so that means when we rearrange that, we're going to get C equals minus 12 times 10 to the 6. Okay, so almost there, we've got one last part to go, which is part D, and which is determine the concentration of salt in kilograms per litre when the tank overflows. Okay, so the tank overflows, okay, when the capacity reaches 300 litres. Okay, so we've then got our volume equation that we had here. Okay, so we can say when our volume equals 300, what's our time? So our time is going to equal 100 minutes. Okay, so we need to substitute in our C value into our equation for Q. Okay, because we know our C value in here, so we can put that in. Okay, and we also sub in our T equals 100. Okay, so we get then that Q of 100 is going to equal 2 outside of 200 plus 100 plus our C value, which is negative 12 times 10 to the 6 over our 200 plus 100 squared. Okay, when we do that, okay, we find that it equals 466 and 2/3 kilograms. Okay, but we need our concentration, okay, and our concentration equals our mass over our volume. Okay, so we know that our mass is our 466 and 2/3 over our volume, which we know is 300 because our tank is full. Okay, which gives a concentration of 1.556 kilograms per litre. Okay, so there can be a little bit to these questions, okay, but we've got a couple more work examples to do still. Okay, so we're going to look at work example 10 now. So a tank contains 5 litres of water in which 10 grams of salt have been dissolved. A salt solution containing 4 grams per litre is poured into the tank at a rate of 2 litres per minute, and the mixture is kept uniform by stirring. Okay, the mixture leaves the tank at a rate of 2 litres per minute. Okay, so we need to go through and we need to think, well, our inflow rate is equal to the outflow rate in this time. Okay, so our V of T, okay, is equal to 2. Now they've written 5. Our V of T, our volume of the tank, sorry, is always equal to 5 litres because that's how much we've got in there initially. Okay, because our inflow and outflow rate's the same, our volume in our container doesn't change. Okay, so our dQ dt, okay, well, that's got to be our inflow rate, take our output rate. So it would be 4 times 2 take 2Q on our V of T. So our dQ dt this time is going to equal 8 minus 2Q on our V, so that's V of T, which is our 5. Okay, so we can simplify that a bit and say that our dQ dt is equal to 2 outside of 20 take Q over our 5. Okay, now remember that that's all we need to worry about there. Okay, so that's for that's our differential equation that was set up. Okay, so we need to solve the differential equation to determine Q at any time. Okay, so that means that we've got to find dt dQ. So it's going to be our 5 over our 2 outside of our 20 minus Q. Okay, so what we need to do, okay, is our separation of variables. Okay, so we're going to say that we've got one of our equations is 5 over 2, and our other equation is 1 over 20 take Q. So we've got to invert this one. So we integrate our 2 on 5 with respect to t, and that equals our 1 over 20 take q with respect to q. Okay, because we always need our two parts here. Okay, well this one has our q part, which means we've got to do this one in terms of t. Okay, so when we do that, then we get 2t on 5, okay, equals negative log to the base e of the modulus of 20 take q, okay, and that's equal to, and we've also got to add on our constant integration. Okay, well we know when t equals 0, our initial concentration is equal to 10. Okay, so we can say t equals 0, so this bit's going to equal 0, we get negative log to the base e of 20 minus 10 plus our c. So our c is going to equal log to the base e of 10, just by rearranging and simplifying. Okay, so we can put that c value back in, and so we can simplify our equation and rearrange it. So we can say our 2t on 5 is equal to negative log to the base e of our 20 minus q plus log to the base e of 10. So we can bring those together, okay, and make it log to the base e of 10 over 20 minus q. Okay, so we do our looping method now, and so we've got e to the 2 on 5t equals now 10 over 20 minus q. Okay, so we can rearrange that and we get our q equals 20 minus 10 e to the negative 2 on 5t by rearranging. Okay, so we've got our solution, our equation there. They just take 10 out and make it 10 outside of 2 minus e to the negative 2 on 5t. Okay, part C, we need to show how much salt is in the tank after 5 minutes and what is the concentration then. Okay, well we need to say let t equal 5, so q is going to equal 10 outside of 2 minus e to the, well, 5 will cancel out with the 5 down there, so we'll just go to the negative 2. Okay, so that means that we end up with a value of 18.646 grams. Now, we need our concentration, so that's our mass over our volume. Okay, so we know our concentration is going to be 18.646 over 5, because our volume is constant at 5 litres, gives us 3.73 grams per litre. Okay, show that the salt solution can never exceed 20 grams. Okay, well, as t approaches infinity, okay, as this gets really, really large, okay, then it approaches, as t approaches infinity, okay, then what we see is that this all approaches 0, okay, and we're left with our q approaches 20. So as t approaches infinity, our q approaches 20, okay, so that's our, really, if you like, our p-value. Okay, so if we sketch the graph then, okay, because remember our p is that value that we can never reach, okay, that we're going to go like this. And our initial concentration was 10, and that value is going to be 20. Okay. So we've got one last worked example to look at, which is worked example 11. Okay. In a biomolecular chemical reaction between 3 grams of a substance A and 6 grams of substance B, the velocity of the reaction, or the speed of the reaction, is proportional to the product of the unused amounts of A and B respectively. A and B combine in equal parts to form substance X. Initially no X is present, but after 3 minutes 3 grams of X have been formed. So what we need to do is set up the differential equation for the amount of substance X at time t. Okay, so we're going to say let X equal X of t. Okay, that would be the amount of grams of substance X formed in t minutes. Okay, so that means that we have our our A plus our B, okay, combined to give us our X. Okay, so the velocity of the reaction is proportional to the product of the unused amounts of A and B. So we can say that our dx on dt, okay, is proportional to, okay, well, we had 3 grams of one substance, okay, and we've got to do our x on 2 because it's half of our x that gets used for combining with each of them. So we can say 6 minus x on 2 as well. Okay, so we can say then that, sorry, that should be dx dt. So we can say our dx dt, instead of being proportional, we can add in a k value, okay, and we can simplify our brackets and make it 6 minus x and 12 minus x, because we can multiply basically through by 2, okay, and we can think then that this our k takes care of everything. Okay, so k is that proportionality. So part B is determine the amount of x present after a further 3 minutes. Okay, well, we need to set up our equation and say we've got our dt dx equals 1 over, sorry, our integral 1 over k times our 6 minus x, 12 minus x dx. Well, we can bring our k out, and sorry, that won't be dt dx, that'll just be t. Okay, so we can bring our k out, okay, and multiply it across, so we can say we've got kt is equal to our integral now of our 1 over 6 minus x, 12 minus x. Okay, so what we're going to have here is an example of partial fractions. Okay, so we can say that our 1 over our 6 minus x, 12 minus x, okay, is equal to some value a over 6 minus x plus our b over 12 minus x. Okay, so when we do our cross multiplication and we're going to expand that out as well, we're going to say that we've got 12a plus 6b minus x outside of a plus b. Okay, so when we compare these, and that's all going to be over our 6 minus x, 12 minus x. So when we compare this to this, well, we can see our constant part is equal to 1. 12a plus 6b is equal to 1. Okay, and also see our variable part is equal to 0. So that means that a plus b equals 0. Okay, so that'll mean that we can say a equals negative b. Okay, so when we solve those simultaneous equations, we just find that a equals 1 on 6 and b equals negative 1 on 6. Okay, so what that means then is we can say we bring this 1 on 6 out. So what we say then is we get kt equals 1 on 6 outside our integral of our 1 on 6 minus x plus 1 on 12 minus x dx. So we've been able to split it up. So that means that our kt is going to equal, we can say negative 1 on 6 log to the base e of our modulus of 6 minus x for the first part. Okay, for the second part, it's going to be plus 1 on 6 log to the base e of the modulus of 12 minus x. Plus we need our constant of integration. Okay, so we can simplify our logs here. We can say, well, kt is equal to 1 over 6 log to the base e of the modulus of 12 minus x on 6 minus x, okay, plus c. Okay, this one's ended up on the bottom because we're the negative here. Okay, so we also know, okay, that initially there was no x in there at all. Okay, so when t equals 0, x equals 0. Okay, so we can say, well, 0 equals 1 on 6 log to the base e of, it'd be 12 on 6, which is 2 plus c. So c is going to equal our negative 1 on 6 log to the base e of 2. Okay, so we can finish setting up our equation and say our kt equals our 1 on 6 log to the base e of our 12 take x on 6 take x, take 1 on 6 log to the base e of 2. Okay, and we can simplify that further with our log laws and say our kt equals 1 on 6 log to the base e of our 12 on, take x on 2 times 6 take x. Okay, so we also know, okay, that when t equals 3 minutes, that we had 3 grams of our product x had formed. So when t equals 3, x equals 3. So I'm going to start running out of room here. So just running through that, okay, we find, when we substitute those in, okay, for k, so when we find k equals 1 on 18 log to the base e of 3 on 2, so that's our k value. Okay, so it gets a little bit messy, but we can rearrange our equation, okay, and we find, okay, that we can get in terms of x. We say, well, x of t equals 12 outside of 1 minus e to the negative 6kt over 2 minus e to the negative 6kt. Now we just haven't put the k's in because k was this log value at the moment. Okay. So what we need to do, okay, is actually, we're almost there, because we need to turn the amount present, okay, of x after a further 3 minutes. So that's going to be when x equals 6. Okay, so when x equals 6, okay, and we've put in this value here for k, okay, we just left it out just to make it a little bit neater. Okay, so if you like, after running that, you can say where k is equal to that. So when we sub in t equals 6 into this with our k value in, okay, we find that we get a value of 37. Okay, so after 6 minutes we have, which when say that it, sorry, is 4 2/7, 8 grams of x. So when say after 6 minutes, okay, we'll have 4 2/7 grams of our product x. Okay, so some of these questions are a little bit involved, okay, but they're all more or less using skills that we've seen before, so hopefully we'll get through the questions okay when you have a look at these worked examples.